At the center of nearly every galaxy sleeps a monster of impossible scale. These are supermassive black holes, gravitational giants weighing millions to billions of times our Sun, and they are not passive. By the end of this exploration, you will understand how these invisible hearts actively build and destroy the galaxies they call home. How can a force known for devouring stars also trigger the birth of new ones? What mysterious feedback decides if a galaxy flames with youth or fades into a red retirement? The answer lies in a violent cosmic ballet of feeding and shaping. What does it mean for our own galaxy that such an engine lies in its quiet core? Their scale is so immense it defies our everyday understanding of size and weight. To truly grasp the nature of a supermassive black hole, we must first separate it from its more common cosmic cousins. The black holes we often hear about are born from the dramatic collapse of a single, massive star. These are stellar mass black holes, and they are powerful, but they are local phenomena, typically weighing between 3 and 100 times our Sun. A supermassive black hole is an entirely different beast. It is a million, a billion, even tens of billions of times heavier than our Sun, a weight so colossal it cannot be explained by the death of a single star. This fundamental difference in scale points to a deeper, more intertwined history. It suggests these giants did not simply fall into the centers of galaxies. They grew up with them, their fates woven together from the universe's earliest chapters. To understand their influence, we need to visualize their boundaries. Every black hole, regardless of size, is defined by its event horizon. Think of this not as a solid surface, but as a point of no return, an invisible spherical boundary in space. Once anything light, gas, even a star crosses this threshold, it is gone forever from our observable universe. The size of this sphere is called the Schwarzschild radius. For a stellar black hole, this sphere might be just a few miles across, but for a supermassive giant, this boundary can be enormous. The event horizon of the black hole at the center of our own Milky Way would comfortably fit inside the orbit of Mercury. For the famous black hole in galaxy M87, with a mass of 6.5 billion suns, its event horizon is still smaller than our entire solar system. This is the paradox that reveals their true nature. They pack an almost incomprehensible mass into a relatively tiny volume, creating a gravitational grip of unimaginable intensity right at the galaxy's core. This extreme concentration of gravity is the anchor of the entire galactic system. Stars many light years away feel its persistent, guiding pull, orbiting the center in a slow, stately dance. It is this gravitational hand, unseen but undeniable, that first shapes the galaxy's overall architecture, holding billions of stars in a coherent, swirling disk or a vast elliptical cloud. But this is merely the passive, structural role. The real mystery and the source of their true power begins when this anchor is not just holding things in place, but actively feeding. What happens when the silent heart of a galaxy wakes up and begins to consume? That silent, gravitational anchor becomes a brilliant beacon when it starts to eat. The primary feeding mechanism of a supermassive black hole is a structure of breathtaking violence and beauty known as an accretion disk. This is not a calm, orderly ring like Saturn's. It is a churning, superheated maelstrom, a cosmic whirlpool where gas, dust, and even the occasional unlucky star are shredded and stretched into a thin, furious disk. Think of it as the black hole's dinner plate, but one where the meal is cooked at temperatures of millions of degrees. The friction within this spiraling material, combined with incredibly powerful magnetic fields twisted into knots, heats it to such an extreme that it does not just glow, it screams. It emits a torrent of radiation across the entire electromagnetic spectrum, from X-rays to visible light, often outshining every single star in its host galaxy combined. When this happens, astronomers call the galaxy's core an active galactic nucleus, a sign that the sleeping monster is wide awake and feasting. The physics of this process is a story of energy conversion on a galactic scale. Everything in space possesses something called angular momentum, a tendency to keep spinning or orbiting. For material to fall into the black hole, it must lose this momentum. It does so through a slow, inward spiral within the disk. As each particle of gas or dust moves closer to the event horizon, it trades its gravitational potential energy, the energy it had by being up high in the black hole's gravitational well, for motion and heat. This conversion is staggeringly efficient, far more so than nuclear fusion in a star. A significant portion of the infalling mass is transformed into pure radiation that blasts outward. This is why such a small, central engine can outshine an entire galaxy of hundreds of billions of stars. But this feast is never a quiet, steady affair. The accretion disk is a place of immense instability. Magnetic field lines frozen into the hot plasma get stretched and tangled until they snap and reconnect in violent events, launching enormous flares of energy. Clumps of material can collide, creating bursts of brightness. The entire disk can flicker and pulse, its light curve telling astronomers a story of chaos and turbulence happening just outside the point of no return. This violent ballet of feeding does more than just create a brilliant light show. It marks the beginning of the black hole's active role in shaping its home. The intense radiation pouring from this cosmic forge is the first and most direct way the black hole begins to push back against its own galaxy, a force that can both give life and take it away. But the black hole's appetite is not satisfied by a steady diet of gas alone. Sometimes it craves something more substantial. A star orbiting peacefully for billions of years can have its path disturbed. A gravitational nudge from a passing star, a subtle shift in the galactic dance, and its fate is sealed. It drifts too close to the invisible giant at the center. What happens next is one of the most violent and luminous events in the cosmos, a tidal disruption event. This is the black hole's stellar snack, a catastrophic and brilliant feast. The star does not simply fall in. Long before it reaches the event horizon, the difference in gravitational pull between the side of the star facing the black hole and the side facing away becomes overwhelming. This tidal force, the same force our moon uses to gently raise Earth's oceans, is amplified here to an unimaginable extreme. The star's own gravity, the force that has held it together for its entire life, is utterly defeated. The star is stretched, pulled apart into a long, thin stream of superheated gas, a process astronomers vividly call spaghettification. It becomes a cosmic noodle of stellar material. Part of this stream is flung away into the darkness of interstellar space, a lost remnant of the star, but a significant portion of the debris rains down onto the waiting accretion disk, providing a sudden, massive infusion of fuel. The observational signature of this event is unmistakable. Astronomers witness a brilliant, multi-wavelength flare that can, for a brief time, outshine every star in its host galaxy. There is a sharp, dramatic rise in brightness across the spectrum, from X-rays to visible light, as the stellar material is ripped apart and heated. Then, over the course of months or even years, that brilliance gradually fades as the last of the debris spirals in and is consumed, a long, slow decay of light marking the end of a star. These events are more than just spectacular fireworks. They are crucial for understanding how black holes, especially the quiet ones in dormant galaxies, manage to grow. In a galaxy where the central black hole is not actively feeding on gas, a single tidal disruption event can provide a feast that adds significant mass, a direct probe that reveals the presence of a dormant giant. This dramatic process shows us that feeding is not always a smooth, continuous flow. It can be episodic, catastrophic, and utterly transformative, sending literal shockwaves of energy through the galactic core that ripple out and influence everything around it. This torrent of radiation is only one way the black hole broadcasts its power. Some feeding giants channel their fury into something far more focused and destructive. When conditions are right, a supermassive black hole can launch twin beams of searing plasma directly from its poles, punching out of the galaxy at nearly the speed of light. These are relativistic jets, nature's own particle accelerators, and they stretch the concept of influence to an intergalactic scale. They do not just shine, they physically push. The energy required is staggering, siphoned directly from the chaos of the accretion disk and the black hole's own spin. As matter spirals inward, it drags incredibly powerful magnetic field lines with it, twisting them into tight, rotating coils around the black hole's axis. Think of a figure skater pulling their arms in to spin faster, but on a scale where the skater is a singularity, and the arms are magnetic fields containing the energy of suns. These fields, wound up to the breaking point, find an escape route along the path of least resistance, the black hole's rotational poles. Here, they act like a colossal electromagnetic slingshot, funneling and accelerating charged particles to velocities so high they defy classical physics. We can see these jets because the particles, racing along magnetic highways, emit a brilliant synchrotron radiation, most famously observed as vast lobes of radio waves that can dwarf the galaxy that created them. The sheer power they carry is almost beyond comprehension, equivalent to the energy of billions of supernovae channeled into two narrow, precise beams. But these are not just spectacular cosmic searchlights. They are active mechanical agents that reshape entire galactic neighborhoods. When a jet plows into the thin gas that exists between galaxies, it shocks and heats that material to millions of degrees, preventing it from ever cooling down and collapsing to form new stars. It can blow gigantic bubbles in the intergalactic medium, carving out cavities that last for eons. This means a single active black hole, through these jets, can impose a star formation drought across distances hundreds of times larger than its host galaxy. It is a direct physical feedback loop where the act of feeding at the center creates a force that reaches out and dictates the future of stellar birth far into the galactic outskirts. The monster does not just live in the heart of the galaxy, it actively gardens its entire domain, and sometimes that gardening involves a cosmic blowtorch. The brilliance of the feeding black hole is not its final word, but its opening argument in a cosmic debate. This argument takes the form of a powerful wind, a gale of energy and matter that rushes out from the furious accretion disk at a significant fraction of light speed. These are Aegean winds, and they are the black hole's way of speaking back to its own galaxy, a conversation that can decide the fate of billions of future stars. The physics is a direct consequence of all that violent feasting. The intense radiation pouring from the disk does not just travel outward as light. It carries momentum, physically pushing against the surrounding clouds of gas and dust, the very raw materials for star birth. It is like standing too close to a rocket engine, not just feeling the heat but being pushed back by the sheer force of the exhaust. This radiation pressure can accelerate material to astonishing speeds, driving it out of the galactic core in a vast, hot outflow. But there is another, even more forceful mechanism. Magnetic fields, twisted and amplified in the accretion disk, can act like colossal slingshots, launching jets of plasma along the poles, but also contributing to broader, less focused winds that billow out in all directions. These outflows are not gentle breezes, they are tsunamis of superheated gas, capable of sweeping through the heart of a galaxy and fundamentally altering its ecosystem. The effect is profound and for star formation devastating. Stars are born when cold, dense clouds of molecular gas collapse under their own gravity. The Aegean wind, however, is hot and fast. When it slams into these stellar nurseries, it does two things. First, it violently heats the gas, preventing it from cooling down and condensing. Second, it can physically push the gas right out of the galaxy, stripping away its future fuel supply. It is a galactic-scale form of gardening where the gardener uses a cosmic blowtorch to clear the soil, preventing any new seeds from taking root. Astronomers have seen the evidence of this dramatic process written across the sky. Telescopes like the Chandra X-ray Observatory peer into the hearts of massive galaxies and see something remarkable. They observe vast bubbles and cavities sculpted in the hot gas that surrounds the galaxy, regions that have been carved out and pushed aside by these relentless outflows. The Hubble Space Telescope, observing invisible light, has captured images of galaxies where gas is being expelled in glowing, cone-shaped winds, a direct visual testament to the black hole's influence. This creates a self-regulating cycle, a feedback loop of astonishing precision. As the black hole feeds on gas, it grows more active and powerful. That power drives winds that heat and expel the surrounding gas. With less gas available, the black hole's own food supply dwindles and its activity begins to wane. The winds calm, allowing gas to slowly cool and accumulate once more, potentially restarting the cycle millions of years later. This negative feedback acts like a cosmic thermostat for the galaxy. It prevents the galaxy from converting all its gas into stars in one furious, brief burst of creation. Without this regulating hand, the most massive galaxies would theoretically grow even larger, forming far more stars than we actually observe. The black hole, through its very act of consumption, sets a limit on the growth of its own home. It is a paradox of creation through destruction, where the engine that devours also preserves the balance, ensuring the galaxy does not burn through its future in a single, brilliant flash. Yet this destructive wind is only one side of the conversation. The black hole's influence holds a profound duality, a capacity for creation that emerges directly from its most violent acts. Those same relativistic jets, capable of sterilizing entire galactic neighborhoods, can under the right conditions become the architects of new stellar life. This is the second paradoxical feedback loop where destruction gives birth to creation. When a powerful jet moving at nearly the light speed does not slam into thin intergalactic gas, but instead plows directly into a massive, dense cloud of molecular material within its own galaxy, the outcome changes completely. The jet does not simply blow the cloud away. Instead, it acts like a cosmic snowplow, ramming into the cloud and sending immense shock waves reverberating through its cold interior. These shock waves are tsunamis of pressure traveling through the gas and violently compressing it. In the chaotic wake, pockets of gas are squeezed past a critical threshold. Their own gravity, now aided by this external crushing force, suddenly wins the battle against internal pressure and heat. These compressed knots begin to collapse, igniting the fires of nuclear fusion and lighting up as brand new stars. This process, observed by astronomers and dubbed Jet-Induced star formation, paints a stunning picture. We see it in vivid telescopic images, where brilliant strings of young, blue stars are found lined up like pearls on a string, tracing the very path where a jet has recently passed through a galactic gas cloud. It is a direct, observable link between the black hole's fury and a sudden burst of stellar birth. One of the most compelling examples of this lies not within a single galaxy, but in an intergalactic interaction. Astronomers point to a peculiar dwarf galaxy known as Minkowski's object. This small, irregular collection of stars and gas shows all the signs of a violent recent starburst, a wave of frantic star formation. And pointing directly at its heart is a relativistic jet, not from its own core, but from a massive neighboring elliptical galaxy. The evidence strongly suggests that millions of years ago, this jet from the neighboring giant slammed into a primordial gas cloud drifting in intergalactic space. The resulting shock compression triggered the collapse that built Minkowski's object itself, essentially using the black hole's power to construct an entire new galactic companion from raw materials. This breathtaking duality forces us to revise our understanding of the cosmic monster. It is not merely a destructive force or a passive anchor. It is a dynamic sculptor whose tools of heat and pressure and sheer kinetic force can both erase and etch new structures into the fabric of its galaxy. The same hand that holds a quenching blowtorch also wields a chisel that can trigger new forms. This complex role, balancing creation against destruction, suggests these giants are integral to the very architectural evolution of galaxies, seeding new stellar populations in their wake even as they suppress others. But this delicate balance of power raises a crucial question. What happens when the feeding becomes too extreme, when the black hole's influence tips decisively toward one side of this cosmic scale? This delicate balance between creation and destruction is not random chaos. It is a finely tuned cosmic engine, a galactic metabolism that regulates the life cycle of an entire star system. The relationship between a supermassive black hole and its galaxy operates like a biological feedback loop, where the rate of feeding is precisely balanced by the energy output it produces. The black hole consumes gas, grows more powerful, and in doing so, switches on its own regulatory mechanisms. The intense radiation and powerful winds that blast outward from its feast begin to push back on the very clouds of gas that are falling in to feed it. If the black hole feeds too greedily, too quickly, it essentially flips a switch that cuts off its own supply line. The resulting feedback heats and disperses the surrounding fuel, starving the engine and causing its brilliant activity to gradually fade into a quiet, dormant state. This self-regulation is so precise that astronomers have discovered a remarkable correlation across the universe. The mass of a galaxy's central, supermassive black hole is not a random number. It is intimately linked to the properties of the galaxy's central bulge, the dense swarm of older stars at its heart. The more massive the bulge of stars, the more massive the black hole. This is not a coincidence. It is a fossil record of that metabolic relationship, evidence that the growth of the star cluster and the growth of the invisible monster were choreographed together over billions of years. Theoretical models that simulate galaxy evolution have brought this story to life. By programming the laws of physics into vast supercomputers, scientists can watch this cycle play out across cosmic time. They begin with a young galaxy rich with cold gas. The central black hole, small at first, begins to pull in that fuel, igniting into an active, brilliant phase. For millions of years, it feasts and shines, but in doing so, it drives powerful outflows. These outflows sweep through the galactic core, clearing away the gas. With its food supply diminished, the black hole's activity wanes. It enters a long period of quiescence, a dormant sleep that can last for hundreds of millions of years. During this quiet era, gas can slowly trickle back into the center, cool, and begin to accumulate once more, setting the stage for the next awakening. The simulation shows this not as a one-time event, but as a repeating pulse, a heartbeat of activity and rest that continues for the lifetime of the galaxy. Each burst of feeding adds a little more mass to the black hole and shapes the stellar population around it, incrementally building that observed correlation between the monster and its home. This cosmic equilibrium is the ultimate governor. It ensures that neither the black hole nor the galaxy can grow in an unchecked, runaway fashion. The black hole's own power places a limit on its growth, while simultaneously regulating the rate at which the galaxy can form new stars. It dictates the galaxy's entire evolutionary path, determining whether it will be a vibrant, star-forming spiral or a quiet, red and dead elliptical. The invisible heart does not just live within the galaxy, it actively manages its metabolism, its growth, and its very destiny. This raises a final, deeply personal question for us, living in a quiet spiral galaxy. If this metabolic cycle dictates the fate of all galaxies, where does our own Milky Way fall within this grand cosmic rhythm? Our own galaxy, the Milky Way, currently sits in the quiet phase of this cosmic metabolism. Its heart, a supermassive black hole named Sagittarius, a star, is mostly dormant, a sleeping giant that offers us a front-row seat to observe the aftermath of these cycles. But to understand the full story of how black holes feed and shape galaxies, we must look far beyond our own quiet corner. We must learn to observe the invisible. Since a black hole itself emits no light, astronomers have become cosmic detectives, mastering the art of studying shadows and echoes. They piece together the diet and influence of these giants by observing the brilliant, violent effects they have on everything around them. One of the most fundamental techniques is simply watching the light. An active galactic nucleus is not a steady beacon. Its brightness flickers and flares dramatically over timescales ranging from hours to years. This variability is a direct window into the chaotic dynamics of the accretion disk itself. Rapid flickering on the order of hours tells astronomers about processes happening extremely close to the event horizon, in regions of space where gravity warps time itself. Lower, larger changes in brightness can signal a tidal disruption event, the feast of a star, or a major shift in the rate of gas falling in. By meticulously monitoring these changes across different wavelengths of light, scientists can map the structure and physics of the feeding process without ever seeing the black hole directly. But light's intensity is only part of the story. Its color, or more precisely its spectrum, holds the secrets of motion. This is where spectroscopy becomes an indispensable tool. When astronomers pass the light from an active galaxy through a spectrograph, they don't just see a rainbow. They see specific dark or bright lines at certain colors, the fingerprints of chemical elements like hydrogen or iron. In the vicinity of a feeding black hole, these lines are not neat and orderly. They are dramatically stretched and blurred. Some are shifted far toward the blue end of the spectrum, indicating gas rushing toward us at thousands of miles per second. Others are shifted to the red, showing gas fleeing away at similar incredible speeds. This is the direct observational signature of those powerful Aegean winds, the bi-directional tsunami of material being blasted outward by the black hole's radiation. Spectroscopy allows astronomers to measure the speed, density, and mass of these outflows, quantifying the very force that regulates galactic growth. To see the structures themselves, however, requires a different kind of vision. For the vast radio lobes powered by relativistic jets, astronomers use interferometry. This technique links multiple radio dishes across a continent or even the globe, creating a virtual telescope as wide as the distance between them. The Very Large Array in New Mexico is a famous example. Its 27-dish antennas working in concert to produce exquisitely detailed images of these gigantic, energetic structures. These radio maps show the jets bending and interacting with intergalactic gas, and the massive lobes where the jet's energy is finally deposited, painting a clear picture of how black holes inject energy into their surroundings on a truly intergalactic scale. The ultimate frontier, of course, is to see the shadow of the event horizon itself. This monumental achievement required turning the entire Earth into a telescope. The Event Horizon Telescope collaboration synchronized radio observatories from the South Pole to Hawaii to Spain, creating a planet-sized interferometer. In 2019, it revealed the now iconic image of the shadow of the supermassive black hole in galaxy M87, a dark circle silhouetted against the glowing accretion disk. This was not a direct photo of the black hole, but an image of its gravitational footprint, the absence of light where light should be. It provided stunning, direct confirmation of Einstein's predictions and opened a new era of studying the extreme physics just outside the point of no return. These tools are constantly evolving. The Chandra X-ray Observatory peers into the hearts of galaxies to see the multimillion-degree gas heated by black hole outflows. The upcoming Nancy Grace Roman Space Telescope will conduct vast surveys to catch black holes in the act of tidal disruptions and trace the history of their growth across cosmic time. Each observation, from a flicker of light to a shadow in the radio waves, is a piece of data that transforms theoretical concepts into observable phenomena. It is through this patient, ingenious detective work that we move from wondering about invisible monsters to understanding the fundamental engines that have shaped the universe we see today. The brilliance and violence we observe are orchestrated by a hidden force. While gravity pulls matter toward the black hole, it is magnetism that directs the final, furious act. These invisible magnetic fields, woven through the superheated chaos of the accretion disk, are the true architects of the black hole's power. They do not just exist, they are generated and amplified by the disk's own turbulent motion, like a dynamo spun by a cosmic hurricane. As the disk churns, these magnetic field lines are stretched, twisted, and braided into ropes of immense tension. They become the fundamental conduits that channel the black hole's energy outward, transforming a simple inward fall into a spectacular galaxy-shaping display. Their most famous role is launching the relativistic jets. This process is driven by the black hole's own spin, a rotational energy that magnetic fields can literally steal. Imagine the black hole as a spinning magnet, dragging the fabric of space-time around with it. The magnetic field lines anchored in the surrounding accretion disk get caught in this whirlpool and wound up like an over-tightened spring. The energy stored in these wound-up fields becomes so immense that the only release is along the black hole's rotational axis, where resistance is lowest. Here, the fields act as a rigid funnel, accelerating charged particles to nearly the speed of light and launching them into space in two opposing beams. This mechanism for extracting a black hole's rotational energy is formally known as the Blandford-Zienagic process, and it is the theoretical engine behind the most powerful jets in the universe. But magnetism's influence is not limited to the poles. Deep within the accretion disk itself, these tangled fields are essential for solving a fundamental puzzle. Matter in the disk wants to orbit the black hole forever, held in place by its angular momentum. To spiral inward and finally be consumed, it must lose that momentum. Primary agent for this transfer is not simple friction, but magnetic stress. The tangled field lines create a kind of magnetic viscosity, a sticky resistance between adjacent layers of the swirling gas. This resistance allows outer, slower-moving material to tug on inner, faster-moving material, slowing it down and allowing it to sink closer to the event horizon. In essence, the magnetic fields act as a cosmic brake, controlling the very rate at which the black hole feeds. Without this magnetic viscosity, the accretion disk would be far less efficient, and the brilliant glow of an active nucleus would be a much dimmer affair. This invisible architecture extends to the broader outflows as well. The same magnetic fields that help launch the focused jets can also contribute to the wider, hotter winds that billow out from the disk. They provide an additional slingshot, helping to accelerate gas to tremendous speeds and ensuring that the black hole's influence reaches every corner of the galactic core. From regulating the meal to launching the leftovers with unimaginable force, magnetic fields are the indispensable middleman in the entire feeding cycle. They are the reason a black hole's dinner is not a quiet, dark affair, but a luminous, galaxy-altering event. Their silent lines of force are the threads that stitch together the black hole's destructive appetite and its creative influence, proving that in the cosmos, the most powerful sculptors are often the ones we cannot see. This shared history is etched into the stars themselves, a cosmic fingerprint of partnership. For decades, astronomers have noticed a strange and precise pattern. In galaxy after galaxy, the mass of the central supermassive black hole is not a random number. It is intimately linked to the properties of the galaxy's central bulge, that dense, spherical swarm of older stars at the galactic core. Specifically, the more massive the black hole, the faster the stars in that bulge are moving. This velocity dispersion, a measure of the random speeds of those stars, tells us about the depth of the gravitational well they orbit within. The tightness of this correlation is startling. It strongly suggests that the growth of the invisible monster and the growth of the visible star cluster were choreographed together, step by step, over billions of years. They did not evolve independently. One fundamentally shaped the other, but which came first? Did the black hole build the bulge, or did the bulge feed the black hole? This chicken or egg mystery is at the heart of understanding galactic evolution. The leading theories paint a picture of a dynamic, two-way street. One compelling idea is that the black hole grows first, acting as the primary regulator. In this scenario, early in a galaxy's life, vast reservoirs of gas collapse toward the center. The nascent black hole feeds voraciously, igniting as a brilliant quasar. But as we've seen, that brilliance comes with a cost. The resulting radiation and powerful winds blast outward, heating and dispersing the surrounding gas. This not only shuts down the black hole's own food supply, quenching its activity, but also halts the formation of new stars in the central region. The black hole, through its very feast, dictates the final mass of the stellar bulge that forms around it. It sets the ceiling. The alternative view focuses on the violent drama of galactic mergers. When two galaxies collide, their gravitational dance funnels enormous amounts of gas and stars directly toward the newly combined core. This provides a sudden, catastrophic feast for the central black hole, causing it to balloon in mass. In this case, the galactic merger builds the bulge through the collision and tidal forces, and simultaneously delivers the feast that grows the black hole to a corresponding size. The truth likely involves both processes, a feedback loop where mergers trigger feeding frenzies, and those frenzies then regulate further growth. We see the most intense chapters of this codependent history written in the deep past. The early universe, just a few billion years after the Big Bang, was a time of incredible violence and brilliance. This was the epoch of peak quasar activity, when supermassive black holes in young galaxies were feeding at a ferocious rate, shining with the light of a trillion suns. These quasars were not just beacons, they were engines of change, actively shaping their infant galactic homes during their most formative years. The vast energy they released likely played a crucial role in heating intergalactic gas, preventing it from collapsing into endless new generations of dwarf galaxies and helping to establish the large-scale structure of the cosmos we see today. This period of rapid black hole growth coincided directly with the era when the most massive galaxies were assembling their stars. The partnership was in overdrive. This means the story of a galaxy cannot be told without the story of its heart. To trace how a majestic spiral or a vast elliptical came to be, we must first decipher the life cycle of its central black hole. Every quiet giant like our own Sagittarius, a star, carries the fossil record of past feasts and explosive growth. The correlation between its mass and the motion of the stars around it is the enduring signature of that ancient dialogue, a story written not in words but in gravity and light. This realization transforms our view of galaxies from static islands of stars into dynamic ecosystems, with a powerful, invisible engine at their core governing their growth, their structure, and ultimately their fate. If the black hole's past activity is imprinted on the galaxy's present state, what does the future of this partnership hold, especially for a galaxy like our own? The most brilliant chapters in a black hole's life were written long ago, Billions of years in the past, the universe was not a place of quiet spirals and settled giants. It was a cosmic construction site, violent and raw, lit by the most dazzling beacons ever to shine. These were quasars, the ultimate expression of a supermassive black hole's power. A quasar is not a different kind of object. It is an active galactic nucleus pushed to its absolute extreme. A supermassive black hole feeding with such voracious, unchecked gluttony that its brilliance can outshine 1 trillion stars combined. For a time, these objects were the most luminous things in the entire cosmos. Their light, traveling for over 12 billion years, still reaches our telescopes today, offering us a direct window into the universe's tumultuous youth. The formation of a quasar is a story of cosmic catastrophe and opportunity. In the dense, gas-rich early universe, galaxies were constantly colliding and merging. When two large galaxies smashed together, their gravitational dance did something extraordinary. It stripped away the orderly orbits of stars and gas, funneling unimaginable amounts of raw material directly toward the newly combined core. This was not a gentle trickle of fuel. It was a catastrophic flood, a delivery of enough gas to feed a black hole for millions of years at a rate far beyond anything we see in the modern universe. The black hole at the center, perhaps already sizable from earlier growth, found itself at the center of a gravitational maelstrom of food. It began to consume at a ferocious pace, igniting its accretion disk into a furnace of such intensity that it became a quasar. The energy released is almost beyond description. A single quasar can be thousands of times brighter than our entire Milky Way galaxy, all that light pouring from a region not much larger than our solar system. This incredible compactness is what makes them such perfect beacons. Because they are so small and so bright, they appear as star-like points of light in even the most powerful telescopes, hence their name, a shortening of quasi-stellar radio source. Their light cuts across the vastness of space, allowing astronomers to use them as backlights. By analyzing how a quasar's light filters through the gas clouds between galaxies, scientists can map the large-scale structure of the early universe, studying the cosmic web in its infancy. But quasars were far more than passive lighthouses. They were the primary growth spurt for the universe's supermassive black holes. This era of peak quasar activity, which occurred when the universe was just a few billion years old, is when these giants likely gained most of their enormous mass. Every feast, however, comes with consequences. The unbelievable outpouring of radiation and wind from a quasar was a feedback mechanism of almost unimaginable power. As the black hole gorged itself, it blasted its host galaxy with energy, heating and expelling the very gas that was feeding it. This self-regulating fury is thought to have played a decisive role in shaping the first generations of massive galaxies. It may have shut down star formation in their cores prematurely, helping to create the vast, red, and dead elliptical galaxies we see today, galaxies whose star-forming days ended long ago. The quasars themselves eventually faded as their fuel supply was exhausted or dispersed, leaving behind the quieter, supermassive black holes we find at the hearts of galaxies now. They were the brilliant, violent adolescents of these cosmic monsters, a phase of explosive growth that set the gravitational foundations for the more settled galactic systems that would follow. Their fading light marked a transition in cosmic history, from a universe of chaotic, brilliant construction to one of slower, more structured evolution. The brilliant quasars of the ancient cosmos have long since faded into quiet. Across the universe today, the majority of supermassive black holes are not blazing beacons, but dormant giants slumbering in the hearts of their galaxies. Our own Milky Way offers the perfect example. Sagittarius, a star, the 4 million solar mass titan at our galactic center, is not a brilliant quasar. It is a quiet shadow, a cosmic engine idling at a fraction of its potential power. This state of quiescence is not an accident, but the final, stable phase of the great feedback cycle. Dormancy occurs when the conditions for a feast simply vanish. Often, it is the black hole's own past violence that creates its present silence. Earlier episodes of intense activity, with their powerful winds and radiation, have swept the galactic core clean of the cold, dense molecular gas that serves as the primary fuel. The pantry is empty because the cook, in a previous frenzy, blew the doors off the kitchen. In other galaxies, the stellar dynamics are simply too stable. Stars and gas orbit in serene, orderly paths that do not funnel material inward toward the waiting gravity well. No traffic jams or collisions occur to send gas spiraling down to feed the beast. And for the oldest, most massive elliptical galaxies, dormancy is a sign of late evolutionary maturity. These galaxies have already converted most of their usable gas into stars, and those stars are now ancient. The era of feasting and furious growth is simply over, leaving behind a quiet giant surrounded by a retired population of stars. So how do we find something that emits almost no light? We watch the things that dance around it. The Nobel Prize-winning work on Sagittarius, a star, provides the textbook method. For decades, astronomers have meticulously tracked the orbits of individual stars whipping around the Milky Way's center at speeds exceeding 10 million miles per hour. By applying the simple laws of orbital motion, just as we would for planets around the Sun, they could calculate the mass of the invisible object they were circling. The result was inescapable. An immense mass of about 4 million suns was confined to a region smaller than our solar system. The only possible explanation was a supermassive black hole. This gravitational detective work, observing the frantic waltz of stars under an invisible partner's lead, is how we confirm the presence of dormant titans in galaxy after galaxy. Their silence does not mean they are powerless. Their immense gravity still governs the orbits of every star in the central bulge, maintaining the galactic architecture. And dormancy is not necessarily permanent. It is a long pause, not a finale. The potential for awakening always remains. Should a fresh cloud of gas be stripped from a satellite galaxy, or should a star's orbit be perturbed into a fatal dive, the dormant giant can stir. We see this in other galaxies, where a sudden, bright X-ray flare betrays the consumption of a small asteroid or a trickle of gas, a minor snack that reminds us the engine is still there, waiting. This cycle of activity and quiescence is the heartbeat of a galaxy, a rhythm set by the availability of fuel and the memory of past outbursts. Our Milky Way's current quiet phase is just one chapter in a much longer story, a period of calm that allows life in its spiral arms to flourish undisturbed. But this calm raises a profound and personal question. If our galaxy's heart has slept through human history, what might it take to wake it? The shape of a galaxy tells a story of its past, a record of forces in balance or in conflict. That final, macro-scale architecture, whether it's a smooth elliptical, a barred spiral, or a grand design whirlpool, is not preordained. It is the result of a dynamic conversation where the central black hole's voice is a powerful, shaping whisper. The energy blasting from a feeding giant does more than regulate star formation. It can sculpt the very skeleton of its home. Consider the classical bulge, that dense, spherical swarm of old stars at the heart of many galaxies. Its very shape is a clue. To maintain that puffed-up, three-dimensional structure, the gas in the central regions must be kept hot and agitated, preventing it from settling down into a cold, orderly disk. This is where active galactic nucleus feedback acts as a persistent heating source. The winds and radiation from the black hole's feast stir up the central cauldron, like a spoon constantly swirling a pot, keeping the material from cooling and collapsing into a flat plane. In this way, a historically active black hole can help forge and maintain the signature bulge, imprinting a round, featureless core onto the galaxy's profile. Now look at the opposite end of the spectrum, a majestic grand design spiral. Its delicate, sweeping arms are patterns of density, waves of compression rolling through a thin, cold disk of gas and stars. For these fragile structures to persist, the galactic disk must remain relatively calm and cool, a quiet pond where gravitational ripples can propagate. A supermassive black hole in a constant state of violent eruption would be like throwing boulders into that pond, heating and disrupting the disk, washing away those beautiful spiral patterns. Therefore, the persistence of a grand design spiral like our own Milky Way suggests its central engine has been quiet for a very long time, allowing the disk to settle and those iconic arms to form and endure. The influence goes even deeper into the dynamics of the disk itself. Many spirals, including our own, feature a central bar, a straight, elongated structure of stars cutting through the galactic core. These bars are not static. They form naturally from instabilities within the disk, and crucially, they act as cosmic fuel lines, funneling gas inward toward the central regions. But what happens when that funneled gas reaches a hungry black hole? Advanced computer simulations reveal a fascinating feedback loop. As the bar drives gas inward, it can trigger black hole activity. The resulting outburst of energy then heats and inflates the gas in the very center, destroying the precise gravitational conditions that maintain the bar itself. The simulations show that strong Aegean feedback can suppress the formation of a new bar, or even cause an existing one to weaken and dissolve over time. The black hole, in essence, can sever the very pipeline that feeds it. This creates a profound link from the microphysics of an accretion disk to the macro-scale sky we observe. A galaxy's morphology becomes a fossilized record of its central engine's historical activity. A giant, smooth, elliptical galaxy, devoid of gas and spiral structure, likely hosted a ferociously active quasar in its past, whose final, powerful outburst sterilized and puffed up its form. A magnificent barred spiral, with its ongoing star formation and intricate lanes of dust, speaks of a quieter history, where its central giant has mostly slept, allowing the disk to organize itself into these complex, beautiful patterns. The monster in the core does not just live within the galaxy's structure. Its past behavior is written into that structure, a permanent signature of its power. If the black hole's voice shapes the galaxy's very body, what does it say about the future of our own spiral home? And could that quiet conversation ever turn into a shout? The architecture of a galaxy is not its only legacy. Beyond shaping stars and structures, these cosmic engines perform a more subtle, elemental alchemy. The furious conditions around a feeding black hole act as a crucible for forging the very atoms that make up our world. Within the superheated plasma of the accretion disk and the relativistic jets, temperatures and pressures reach such staggering extremes that nuclear reactions can occur, fusing lighter elements into heavier ones. This is not the slow, steady fusion of a star's core, but a violent, sporadic process. Particles are accelerated to incredible energies, colliding with such force that they can transmute elements, adding protons and neutrons to build up the periodic table from the inside out. Elements like carbon, oxygen, neon, and iron can be synthesized or significantly enhanced in these chaotic environments. The black hole, in its act of destruction, becomes an unexpected creator of chemical complexity. But forging these elements is only the first step. The true magic lies in the distribution. These newly minted atoms are not destined to fall past the event horizon into oblivion. Instead, they are caught up in the powerful outflows, the very same winds and jets that regulate star formation. These energetic rivers of gas act as a galactic delivery system, sweeping the enriched material up and away from the central forge. They carry it high above the galactic plane, injecting it into the vast, sparse halo that surrounds the galaxy, or even ejecting it entirely into intergalactic space. This process is a form of cosmic recycling on the grandest scale. The heavy elements created in the brief, brilliant lives and explosive deaths of earlier stars can fall toward the black hole, be reprocessed in its violent vicinity, and then be launched back out into the galaxy, their chemical signatures altered and enhanced. We can trace the journey of a single atom of iron, perhaps forged in the supernova of a massive star billions of years ago. Drifting through the interstellar medium, it gets swept into the gravitational current flowing toward the galactic center. It enters the maelstrom of the accretion disk, where unimaginable heat and particle collisions might strip it of electrons or even smash it into other nuclei, altering it further. Then, caught in the blast of an Aegean wind, it is propelled outward at a fraction of light speed. For millions of years, it travels through the galactic halo, a solitary traveler from the heart of darkness. Eventually, gravity may guide it back down, where it becomes part of a vast, cooling cloud of molecular gas, a stellar nursery for the next generation. When that cloud collapses to form new stars and planets, that atom of iron, now enriched by its passage near the black hole, becomes part of the raw material. It might end up in the core of a rocky planet or in the bloodstream of a living creature. This means the oxygen we breathe, the carbon in our cells, and the iron in our blood carry within them a history that may have passed through the most extreme environments in the universe. The black hole, through this cycle of chemical enrichment, ensures that galaxies evolve not just structurally, but in their very composition. Each generation of stars is born from gas that is slightly richer in heavy elements than the last, allowing for the formation of rocky planets and the complex chemistry that underpins life. The silent giant in the core is thus a galactic chemist, its violent processes quietly seeding the future with the elemental ingredients for complexity. This raises a profound question about our own place in this cycle. If the elements for life are scattered by such titanic forces, what does that suggest about the story written in every atom around us? This elemental journey forces us to look back to the very beginning, to a fundamental mystery that still puzzles astronomers. How did these supermassive black holes get so big so fast? The most distant quasars we observe, blazing when the universe was less than 1 billion years old, already contain black holes weighing over 1 billion suns. For a black hole to grow that massive in such a short cosmic time, it could not have started from a small seed. It needed a colossal head start. The search for these first seeds is a hunt for the origin story of the monsters themselves. The leading theory points to the very first generation of stars, known as Population 3 stars. These ancient giants, born from the pristine hydrogen and helium of the early cosmos, are thought to have been hundreds of times more massive than our Sun. Their lives would have been spectacularly brief and violent, ending in cataclysmic collapses that left behind black hole seeds of perhaps a few hundred solar masses. While this provides a starting point, the math is challenging. Growing a several hundred solar mass seed into a billion solar mass behemoth in under 1 billion years requires a feeding frenzy that pushes against theoretical limits. The black hole would need to consume gas at its maximum possible rate, almost constantly, without the self-regulating feedback shutting it down. It is a race against time that strains this otherwise elegant model. Another compelling idea skips the star entirely. This is the direct collapse model. Imagine an early galaxy, a dense knot of dark matter and primordial gas. Under just the right conditions, perhaps in a region bathed in intense ultraviolet light that prevents the gas from cooling and fragmenting into many small stars, the entire central cloud could collapse in on itself catastrophically. Without ever igniting as a star, this vast reservoir of gas weighing tens of thousands of suns could plunge directly into a massive dark pit, creating a seed black hole of immense proportions from day one. This kind of seed would have a tremendous advantage, a huge initial mass from which to grow, making the timeline to become a supermassive giant far more plausible. A third pathway is one of relentless consolidation. In the crowded, violent cores of the first protogalaxies, smaller stellar mass black holes could have formed, sunk to the center through dynamical friction, and merged together over and over. This hierarchical building, like rolling snowballs into a giant snowman, could also assemble a sizable seed. Yet this process might be too slow to explain the very earliest quasars, and it requires a densely packed stellar environment that may not have existed in the first few 100 million years. Each hypothesis leaves a different imprint on the cosmos that we might someday detect. The direct collapse seeds, for instance, might be accompanied by a brilliant flash of light as the gas cloud finally plummets inward, a signature future telescopes could hunt for. The mergers of smaller black holes would ripple spacetime with gravitational waves, signals that could be captured by next-generation observatories like the space-based LISA detector. And the properties of the most distant quasars themselves, their exact brightness and growth rates, serve as a stopwatch, telling us how much time their seeds actually had to grow. Unlocking this mystery is the final piece of the co-evolution puzzle. It takes the story from the mature relationship we see in galaxies today, all the way back to the chaotic nursery where the first black holes and the first galaxies were born together. The nature of the seed dictates the initial conditions for that billion-year partnership, setting the stage for everything that followed. The ultimate collision is not one of light but of gravity itself. When two galaxies merge in a slow, billion-year dance, their central supermassive black holes are destined to meet. Drawn together by gravity, they begin a final, intimate orbit, a cosmic waltz that ends with a union of unimaginable power. This merger does not create a flash of light or a burst of radiation. Instead, it sends a shudder through the very fabric of the universe, a ripple in spacetime known as a gravitational wave. To understand this, picture spacetime not as an empty stage, but as a flexible, invisible trampoline. Massive objects like stars and black holes create dips in this fabric. When two incredibly dense objects like black holes orbit each other, they don't just move through space, they whip the trampoline itself. As they spiral inward faster and faster, they create accelerating waves of distortion that radiate outward at the speed of light, stretching and squeezing everything in their path by a minuscule, almost imperceptible amount. The energy released in this final moment of coalescence is staggering, often exceeding the combined light of every star in the observable universe, all channeled into these silent ripples. This is how black holes can grow to even more monstrous sizes, not by feeding, but by literally consuming each other, a direct and violent form of growth that permanently alters the mass of the galactic heart. Detecting these whispers from colliding giants requires a new kind of ear, one that listens not for light, but for the subtle tremor of space itself. Ground-based observatories like LIGO have already heard the higher frequency chirps of stellar mass black holes merging, but the deep, rumbling bass notes of supermassive black hole mergers are a different story. These events produce gravitational waves with wavelengths so long spanning millions or even billions of miles that they wash over our entire planet like a slow cosmic tide. To catch them, we must go to space. That is the mission of the Laser Interferometer Space Antenna, or LISA. Slated for launch in the next decade, LISA will consist of 3 spacecraft flying in a perfect triangular formation, millions of miles apart, connected by laser beams. As a gravitational wave from a distant black hole merger passes through, it will ever so slightly change the distance between these spacecraft, stretching one leg of the triangle and compressing another. By monitoring these laser links with incredible precision, LISA will tune into this low-frequency symphony, allowing us to hear the mergers of supermassive black holes across cosmic time. This won't just confirm they happen, it will let us sense how often galaxies engaged in these monumental marriages, providing a direct history of galactic growth through collision. The aftermath of such a merger can be more dramatic than the event itself. The final burst of gravitational waves is not always perfectly symmetrical. If the two black holes have different masses or are spinning at different angles and speeds, the waves can be shot out more powerfully in one direction. According to Newton's third law, for every action there is an equal and opposite reaction. The black hole itself can recoil from this lopsided blast, like a rocket firing off in one direction. In extreme cases, this gravitational wave kick can be so powerful, reaching speeds of thousands of miles per second, that it ejects the newly formed, even larger black hole completely from the galactic center. Imagine the heart of a galaxy suddenly ripped out. The gravitational anchor for billions of stars is gone, flung into the dark intergalactic void. The consequences for the galaxy are profound. The central region, now devoid of its massive governor, could become unstable. Stars might scatter on new, chaotic orbits. Without the central black hole's regulating feedback, gas could flow in unchecked, potentially triggering a wild, unsustainable burst of star formation or simply falling into disarray. The galaxy's elegant structure, shaped over eons by that central gravity, would begin to unravel, forced to find a new balance around an empty core. This represents the most extreme shaping event possible, where the monster does not just feed or rest, but abandons its throne entirely, leaving its kingdom to an uncertain fate. It is a reminder that the story of a galaxy is written not just in light and gas, but in the silent, gravitational echoes of its most violent chapters. But the story of galactic shaping does not end with the actors we can see or the echoes we can hear. There is another, more pervasive player in this cosmic drama, a silent partner whose gravity writes the rules for everything else. This is dark matter, the invisible framework that holds galaxies together. We cannot see it, touch it, or detect it with light, yet its gravitational hand guides the orbits of stars and the flow of gas, setting the stage upon which the black hole performs. Its vast, diffuse halo envelops every galaxy like an immense, unseen sphere, and within this hidden architecture lies a subtle influence on the monster's appetite. The distribution of dark matter determines the overall gravitational landscape of the galaxy. Think of it as the shape of the valley that a river flows through. If the dark matter halo is particularly dense or has a certain shape, it can shepherd the orbits of stars and gas clouds over millions of years, slowly nudging them on paths that drift inward toward the center. This is a slow, cosmic funneling mechanism, a patient delivery system that can, over eons, ensure a steady trickle of fuel reaches the central regions, even in a galaxy that appears quiet. It is dark matter's overarching gravity that maintains the structure which allows gas to eventually find its way to the core, setting the table for a future feast. Beyond this gravitational guidance, there are more speculative, exotic possibilities. Some theories in particle physics propose that dark matter is not entirely inert. It might consist of hypothetical particles that, when they encounter their antimatter counterparts, annihilate in a flash of energy. And where in a galaxy would such particles be drawn in incredible densities? Precisely at the center, deep within the powerful gravitational well of the supermassive black hole. If these particles exist, they could accumulate in a dense cloud around the event horizon. Their annihilations would release a continuous, faint glow of gamma rays, an exotic power source that does not come from accreted gas or stars, but from the annihilation of the universe's most mysterious substance. While this remains a theoretical idea, it hints at a profound connection between the largest and smallest puzzles in cosmology, the nature of galactic cores and the identity of dark matter itself. This interplay reminds us that the full narrative of a galaxy is woven from both the seen and the unseen. The brilliant fury of the accretion disk, the sweeping jets, and the chemical enrichment are all dramatic acts played out on a stage built by dark matter's silent gravity. To understand why one galaxy feeds its heart violently while another lets it sleep, we must consider not just the visible gas and stars, but the hidden scaffold that organizes them all. It is a humbling realization. The most extreme gravitational phenomena in the universe, the supermassive black holes, may have their diets and their life cycles subtly orchestrated by the universe's most dominant yet elusive component. This pushes our detective work to its very limits, asking us to decipher a story written in invisible ink, guided by a hand we have never truly felt. If dark matter sets the stage and the black hole directs the action, what does this grand production tell us about the ultimate fate of the cosmic theater itself? Our own galactic backyard provides the perfect laboratory for studying a supermassive black hole in its quiet state. Sagittarius, a star, the 4 million solar mass giant at the heart of the Milky Way, is not a brilliant quasar. It is a shadow, a cosmic engine idling so softly that its direct light is drowned out by the glow of millions of surrounding stars. To prove its existence and measure its immense gravity, astronomers became patient detectives, watching the frantic dance of stars in the galactic core for decades. One star in particular, known as S2, became a key witness. Its orbit is a highly elongated ellipse that brings it breathtakingly close to the invisible point at the center. At its closest approach, S2 whips around at speeds exceeding 15 million miles per hour, nearly 3% the speed of light, completing a single orbit in just 16 Earth years. By meticulously tracking this and other stellar orbits, applying the same laws of motion that govern planets around our Sun, scientists performed a simple but profound calculation. They determined that an object with the mass of 4 million suns must be crammed into a region smaller than our solar system. The only possible explanation for such an extreme concentration of mass is a supermassive black hole. This Nobel Prize-winning work gave us the most direct evidence yet for the monster at our galaxy's core, not by seeing it, but by seeing its unmistakable gravitational hand on the stars it commands. This quiet giant, however, is not completely asleep. Even on its lean diet, it occasionally stirs. About once a day, Sagittarius, a star, emits a brief, bright flare in X-ray and infrared light. These are not the brilliant outbursts of a feeding frenzy, but something more like cosmic snacks. Astronomers believe these flares are caused by small clumps of gas, perhaps torn from passing asteroids or shredded clouds, finally crossing the event horizon. Alternatively, they could be the result of magnetic field lines near the black hole snapping and reconnecting, releasing pent-up energy in a sudden flash, like a cosmic version of a static electricity spark. These flickers are incredibly faint compared to an active galactic nucleus, but their detection is crucial. They tell us that even in its dormant phase, the black hole's immediate environment is dynamic, a place where the last vestiges of material are still being siphoned away by that relentless gravity. Studying this low accretion state is like observing a bear in hibernation. Its metabolism slowed to a bare minimum, but its fundamental nature unchanged. It shows us what happens when the flood of gas has been turned off, leaving only a faint trickle to sustain the engine. The environment surrounding Sagittarius, a star, is itself a unique and extreme place, shaped by its long, quiet influence. The galactic nucleus is a densely packed metropolis of stars with orbits arranged in a complex, swirling dance. The black hole's gravity has sculpted this central cluster over billions of years. There is also a faint, hot bubble of gas surrounding the immediate vicinity, likely the lingering echo of past minor outbursts that heated the local material. By mapping this environment in exquisite detail with telescopes like Chandra and the Keck Observatory, astronomers gain a baseline understanding of a galactic core that is not dominated by violent feedback. We see what the architecture looks like when the central engine is switched to a low hum. This makes the Milky Way's center an essential point of comparison. When we look at a brilliant, distant quasar or a galaxy with powerful jets, we can contrast its furious core with our own quiet one. This comparison allows us to calibrate our models to understand how the same fundamental object, a supermassive black hole, behaves under vastly different conditions, from a starvation diet to a gluttonous feast. Ultimately, Sagittarius, a star, offers a profound insight into the long-term life cycle of these cosmic giants and their subtle influence on a spiral galaxy. Its current quiescence is likely a phase, a pause in a cycle that may have included more active periods in the Milky Way's deep past. Each minor flare, each passing snack, is a reminder that the potential for awakening always remains, should a larger cloud of gas ever be funneled its way. For a spiral galaxy like our own, this long quiet period has been essential. The absence of powerful Aegean winds and jets has allowed our galactic disk to remain relatively calm, cool, and structured. It has permitted the beautiful spiral arms to form and persist, and it has allowed molecular clouds to collapse peacefully into new generations of stars and planets, undisturbed by a central tempest. In this way, the sleeping monster has, perhaps paradoxically, been a guardian of stability. Its quiet gravity anchors the central bulge without disrupting the delicate disk, enabling the conditions that, in one unremarkable spiral arm, allowed our solar system to form and life to emerge. Studying Sagittarius, a star, is not just about understanding a distant curiosity. It is about reading the history and forecasting the future of our own galactic home, a story written in the silent motions of stars and the faint, hungry flickers from a dark heart. The iconic first image of a black hole's shadow did more than make history. It gave us a detailed portrait of a cosmic engine in action. That black hole, residing in the giant elliptical galaxy Messier 87, has been a scientific beacon for nearly a century, not for its silhouette, but for the brilliant spear of light erupting from its core. This is M87's relativistic jet, a cosmic searchlight stretching over 5,000 light-years into space, a visible testament to the raw power a feeding supermassive black hole can unleash. Decades of observation have transformed this single jet into a universal laboratory, a natural experiment where we can watch the principles of black hole feedback unfold on a truly colossal scale. Unlike the turbulent spiral of our own Milky Way, M87 is a smooth, gas-poor elliptical, a galaxy whose star-forming days are largely over. This makes its brilliant jet not a creator, but a dominant force of maintenance, a key that helps explain why such massive galaxies remain quiet and red. The jet's very existence is a direct product of the black hole's immense spin and the powerful magnetic fields wound tight by its accretion disk. But how does a chaotic, superheated whirlpool produce such a narrow, straight beam that persists for thousands of light-years without dissipating into a cloud? The secret is a process called collimation. Observations across the electromagnetic spectrum show that the base of the jet is likely funneled and focused by magnetic fields, and perhaps even by the pressure of the hot gas swirling in the innermost accretion flow. It acts like a cosmic nozzle, taking the explosive energy from the core and channeling it into a tight, coherent beam that can punch through the galaxy's atmosphere and far beyond. We can trace this journey by observing the jet in different kinds of light. Radio telescopes like the Very Large Array map the jet's vast, extended structure, revealing where it finally plows into the thin intergalactic gas and splays out into giant, billowing lobes. These radio-bright regions are where the jet's forward momentum is finally halted, its energy dissipated into heating the surrounding medium. But to see the jet's violent heart, we need to look in higher energies. X-ray observations from telescopes like Chandra pinpoint sites of intense shock waves within the jet itself, knots and bright spots where particles are being accelerated to nearly the speed of light. Even gamma-ray telescopes have detected flares from the jet's base, signaling moments of extreme magnetic violence near the black hole. By stitching together this multi-wavelength view, astronomers can follow the beam's energy from its birth at the event horizon to its final galaxy-shaping deposition. The influence of this single jet extends far beyond the boundaries of M87 itself. The galaxy sits at the heart of the sprawling Virgo cluster, a metropolis of thousands of galaxies. The jet and the powerful winds likely flowing from M87's core act as a central heating system for this entire cluster. They pump energy into the super-hot, thin gas that fills the space between the cluster's galaxies, preventing that gas from cooling, collapsing, and forming new stars in vast quantities. This is black hole feedback operating at its most majestic, where a single engine in a single galaxy can regulate the growth and evolution of an entire galactic neighborhood, imposing a calm, settled state that lasts for billions of years. M87's jet is more than a spectacular celestial feature, it is a master key. Its decades of study have illuminated universal rules about how black holes convert spin and gravity into focused power, how that power is transported across intergalactic distances, and how it ultimately governs the climate of the cosmos. This one well-studied beam confirms that the monster in the core is not a passive resident, but an active governor whose voice, whether a whisper or a shout, echoes throughout its entire domain. A single cloud of gas drifting near the galactic center faces a cosmic crossroads. Its future is a tug of war between three powerful forces, and the outcome will write a line in the story of its entire galaxy. The first force is the relentless pull of gravity from the supermassive black hole, an invisible hand constantly beckoning. The second is the cloud's own angular momentum, the inherited spin from the galaxy's rotation that wants to keep it circling forever in a stable, lazy orbit. And the third is the black hole's own voice, the powerful winds and radiation that can blast outward, pushing the cloud away entirely. Which path the cloud takes depends on a delicate contest, and the black hole's current mood is often the deciding factor. If the cloud can shed its angular momentum, its fate is sealed. This is not easy, as space is a near-perfect vacuum with little friction. Instead, momentum is lost through cosmic traffic jams. Cloud might collide with another gas stream, creating turbulence that slows it down. More subtly, magnetic fields threading through the gas can act as a brake, a process called magnetic braking, where the field lines drag against the surrounding medium, siphoning away spin. As the cloud loses this orbital energy, it begins a slow, inevitable spiral inward. It joins the chaotic river of material flowing toward the center, destined to become part of the superheated accretion disk and ultimately fuel for the monster's next meal. This is the primary feeding channel, a slow trickle that can sustain a low level of activity for eons. But not all gas is destined for the plunge. Some clouds find a temporary peace in a gravitational sweet spot. They lose just enough angular momentum to settle into a stable, circular orbit very close to the black hole, but not so much that they continue their fatal spiral. Here, they can accumulate with other gas clouds, forming a spectacular structure known as a circumnuclear ring. These are vast, rotating belts of cold, dense molecular gas, often located just a few hundred light-years from the galactic core. They are crucibles of star formation, lit up by the brilliant blue light of newborn star clusters. In a beautiful twist, this ring represents gas that was funneled toward the black hole but managed to stop just short, choosing creation over destruction. It is a stellar nursery built on the edge of the abyss, a testament to the complex gravitational geography of the galactic center. The third path is the most dramatic expulsion. If the black hole is in an active phase, the cloud's journey is violently interrupted. Long before it can settle into a ring or spiral inward, it is met by the supersonic gale of an Aegean wind. This torrent of energy and hot plasma slams into the cold cloud, shocking and heating it to millions of degrees in an instant. The cloud is not gently pushed, it is shattered and swept up, becoming part of a vast, hot outflow. Its atoms are carried high above the galactic plane in a galactic fountain, a process where ejected gas may eventually cool and fall back down in a distant spiral arm, recycled into the galaxy's ecosystem millions of years later. This path removes the gas entirely from the central fuel reserve, starving both the black hole and the central star-forming regions. The balance between these three fates is not static. It is a dynamic conversation where the black hole argues with itself. A quiet black hole allows gas to accumulate, perhaps forming a bright circumnuclear ring or slowly trickling in to eventually spark a new period of activity. But once that activity begins, the resulting winds actively shut down the very process that feeds it, pushing potential fuel into the fountain and toward the galactic halo. This self-regulation creates the observed cycles of feast and famine. It explains why we see such different structures in different galactic cores, from brilliant rings of young stars to vast, empty cavities scoured clean by ancient outflows. The journey of a single gas cloud, therefore, is a microcosm of the galaxy's metabolic cycle, a simple decision of infall, orbit, or outflow that collectively dictates the growth and destiny of an entire cosmic system. These complex cosmic conversations can be simulated within a supercomputer to unravel the grand narrative of how black holes and galaxies co-evolve. Astrophysicists have built entire digital universes governed by the fundamental laws of physics. These are not simple animations, but colossal mathematical experiments, where every particle of virtual gas and every point of simulated starlight obeys the equations of gravity, fluid dynamics, radiation, and magnetism. The challenge is one of staggering scale. The physics governing a single atom spiraling into a black hole unfolds over microseconds and spans mere kilometers, while the galactic structures shaped by that process evolve over billions of years and across hundreds of thousands of light years. No single observation can capture this entire spectrum, but a supercomputer simulation can attempt to bridge it, modeling the universe from the cosmic web down to the heart of individual galaxies. Projects like the Illustris TNG and FIRE simulations represent the pinnacle of this effort. They begin with the primordial soup of the early universe, a nearly smooth distribution of dark matter and gas, and then set the clock in motion. The code calculates the gravitational pull between trillions of dark matter particles, watching as they clump together to form the invisible scaffolding of the cosmic web. Within these halos, the simulation tracks the complex behavior of the baryonic matter, the ordinary gas that will form stars and black holes. It models how gas cools, condenses, and collapses under gravity to ignite as stars. It calculates the explosive feedback from supernova, which blast energy and enriched material back into the virtual space. And crucially, at the center of each growing galactic potential well, the simulation plants a seed for a supermassive black hole. This is where the true test begins. The code must then simulate the black hole's growth, not as a simple script, but as a consequence of the gas dynamics it creates. As virtual gas clouds are funneled toward the center by galactic mergers or bar instabilities, the black hole accretes mass based on local density and physics-based prescriptions. With growth comes feedback. The simulation injects energy into the surrounding gas, mimicking the effect of radiation pressure and high-speed winds pouring from the active nucleus. The outcome is not predetermined. The scientists watch to see if their mathematical recipe produces a universe that looks like our own. The results are often breathtakingly realistic. When they pause a simulation like Illustris TNG and look at a snapshot of a virtual galaxy, they see structures that mirror Hubble Space Telescope images. Majestic spiral arms, central bulges, and even the distribution of different galaxy types across cosmic time emerge naturally from the interplay of these coded laws. Most importantly, the simulations show the feedback loops in action. They visually demonstrate how a burst of black hole activity creates a hot bubble in the galactic core, pushing gas out and quenching star formation, leaving behind a red, dead elliptical galaxy. They show how, without this regulating feedback, galaxies would grow too massive, too bright, and form too many stars, contradicting what we actually observe in the night sky. These digital laboratories allow for a form of cosmic archaeology. Researchers can rewind a simulation and trace the history of a single galaxy, identifying the exact merger or accretion event that triggered its black hole's most violent outburst. They can run the same initial conditions with the black hole physics turned off and witness a universe that looks fundamentally wrong, proving the indispensable role of these central engines. By comparing the statistical properties of millions of virtual galaxies to vast sky surveys, theorists can refine their models, adjusting the efficiency of feedback or the mechanics of accretion until the digital cosmos aligns with the real one. This iterative process turns abstract theory into a predictive, testable framework. It connects the microscale chaos near an event horizon to the macroscale architecture of the universe, providing a dynamic, evolving picture of how the invisible hearts of galaxies have, quite literally, shaped everything we see. The story of these cosmic engines is far from finished. In the coming decade, a new generation of observatories will open windows into the feeding habits of black holes with a clarity we have only dreamed of. These are not just incremental upgrades. They are revolutionary instruments designed to catch the monster in the act and measure its galactic influence with surgical precision. Each telescope listens to a different part of the cosmic conversation, from the first whispers in the early universe to the present day, echoes shaping galaxies around us. The James Webb Space Telescope, with its unparalleled infrared vision, acts as a time machine. It is already peering back to the era of the very first quasars, studying the light from galaxies so distant their light has traveled for over 13 billion years. Webb's sensitive instruments can dissect the spectra of these infant monsters, analyzing the chemical fingerprints in the gas swirling around them. This allows astronomers to measure their growth rates, study the properties of their host galaxies in their infancy, and search for the environmental clues that might point to how their colossal seeds first formed. Was it from the collapse of primordial gas clouds or the rapid merging of early stars? Webb's data is providing the first direct observations from this foundational epoch. While Webb looks deep, the Nancy Grace Roman Space Telescope will look wide. Its field of view is 100 times larger than Hubble's, allowing it to conduct vast panoramic surveys of the sky. Roman will perform a cosmic census, discovering millions of active galactic nuclei and tidal disruption events that would otherwise be missed. It will map the large-scale structure of the universe and track how black hole activity correlates with the density of their galactic environments over cosmic time. This statistical power is key to understanding the duty cycle of these engines, how often they switch on and off across the lifetime of a galaxy. To feel the heat of the black hole's breath, we will need the Athena X-ray Observatory. Scheduled for launch in the 2030s, Athena will be the most powerful X-ray telescope ever built. It is designed specifically to study the hot universe, the multimillion-degree gas that is the primary signature of black hole feedback. Athena will map the vast cavities and shock fronts sculpted by Aegean winds in exquisite detail, measuring the temperature, density, and velocity of this heated material. It will quantify, for the first time with high precision, exactly how much energy a feeding black hole injects into its surroundings, turning a qualitative concept of feedback into hard, measurable numbers. For the grand, sweeping structures carved by relativistic jets, the future belongs to radio astronomy. The Square Kilometre Array, or SKA, will be the largest radio telescope ever conceived, with thousands of dishes spread across 2 continents. Its sensitivity and resolution will be unmatched, allowing it to image the magnetic field structures within jets in stunning detail, tracing how they channel energy from the black hole's immediate vicinity out to intergalactic space. The SKA will watch jets evolve in real time, observing knots of material brighten and fade as they travel, providing a dynamic movie of how these cosmic blowtorches interact with their environment. Together, this fleet of next-generation eyes will transform our understanding from a collection of snapshots into a continuous, high-definition film. They will test our theories of black hole seed formation by searching for their faint, early signatures. They will clock the feeding cycles of black holes across cosmic history, revealing the rhythm of galactic metabolism. Most importantly, they will trace the journey of energy from the event horizon to the galactic halo with unprecedented fidelity, showing us the exact mechanics of how an invisible heart sculpts its visible home. The narrative of black holes and galaxies, already rich with discovery, is poised for its most thrilling chapters yet, written in data of unimaginable depth and clarity. The journey of an atom from a galactic core to a living cell is a story written across the cosmos. While supermassive black holes seem like impossibly distant monsters, their influence is woven into the very fabric of our existence, answering questions that have echoed in human minds since we first looked up at the stars. This pursuit is far more than an abstract scientific exercise. It is a direct investigation into our own cosmic ancestry and the ultimate fate of our galactic home. By deciphering how these giants feed and shape galaxies, we are essentially reading the biography of the Milky Way. We learn why our galaxy is a majestic, star-forming spiral and not a featureless elliptical void. We can trace the historical pulses of activity from Sagittarius, a star, and forecast what might happen if a fresh cloud of gas is ever funneled to our center. This knowledge transforms the night sky from a static painting into a dynamic, living story, with our solar system playing a small role in a grand narrative authored by gravity. The extreme environments around these black holes serve as nature's ultimate laboratory. Here, gravity is so intense that it warps space-time itself, creating conditions that test the fundamental laws of physics to their absolute breaking point. The conflict between Einstein's theory of general relativity, which governs the very large, and quantum mechanics, which rules the subatomic world, plays out in the chaotic dance just outside the event horizon. By studying the flicker of light from an accretion disk or the shadow cast against hot gas, we are conducting experiments in a regime no Earth-bound lab could ever replicate. This quest to understand pushes the boundaries of human ingenuity, driving remarkable technological leaps. The planet-spanning Event Horizon Telescope, the sophisticated algorithms that process its data, and the supercomputers that simulate galactic evolution are all byproducts of our need to comprehend these dark hearts. The technology developed to see the unseeable often finds its way into our daily lives, improving medical imaging, data networks, and computational power. Perhaps the most profound connection is elemental, written in the atoms that compose you and everything around you. The iron in your blood, the calcium in your bones, and the oxygen you breathe were forged in the hearts of ancient stars. But their journey did not end there. Many of these heavy elements were likely swept up in the powerful outflows from ancient, feeding black holes, carried on galactic fountains and winds that seeded them across the Milky Way. This cosmic recycling means that parts of us were once part of something unimaginably vast and violent, processed through the most energetic engines in the universe before finding their way into a molecular cloud that collapsed to form our sun and its planets. We are not just living in the galaxy, we are literal products of its dynamic, often violent, life cycle. Ultimately, this exploration satisfies a deep and intrinsic human yearning. It is the same drive that sent early navigators across uncharted oceans and now sends our telescopes across the void. To understand the supermassive black hole is to understand the prime architect of galactic destiny, the force that dictates where stars are born and where they die, and how a vast island of billions of suns evolves over cosmic time. In piecing together this story, we locate ourselves within it. We are conscious matter on a small planet, orbiting an ordinary star, in the quiet suburbs of a spiral galaxy whose current peace is guarded by a sleeping giant. This perspective is both humbling and empowering, a reminder that our quest for knowledge is itself a fundamental part of the universe's story, a way for the cosmos to begin to understand its own astonishing nature. From devouring stars to birthing them, these invisible giants are the ultimate conductors of a cosmic symphony. Their story is not one of mindless destruction, but of a dynamic, often paradoxical creativity. We have traced the journey of energy from the chaotic whirlpool of the accretion disk, where matter vanishes forever, out to the sweeping jets that sculpt intergalactic space and the powerful winds that regulate the birth of new suns. This feedback loop is the hidden engine of galactic evolution, a pulse of activity and quiescence that dictates whether a galaxy flames with youthful blue stars or settles into the red retirement of old age. It connects the infinitesimal physics just outside an event horizon to the grand architecture of a galaxy spanning hundreds of thousands of light years. This understanding transforms our view of the cosmos. Galaxies are not static islands adrift in nothingness. They are dynamic ecosystems, living entities that breathe, grow, and change over eons, governed by the powerful heart at their core. The quiet giant in our own Milky Way, Sagittarius, a star, is not an anomaly. It is a chapter in this universal story, a period of calm in a cycle that has likely seen more active eras in the deep past and may see them again in the distant future. Its current slumber is what allows our spiral home to maintain its delicate structure, its star-forming arms, and the stable environment in which our solar system could form. Studying these monsters challenges the very frontiers of physics, forcing us to reconcile the immense scale of gravity with the quantum weirdness of the subatomic world. It drives our technology to new heights, from planet-spanning telescopes to universe-simulating supercomputers, and on a deeply human level, it connects us to the cosmos in a tangible way. The elements that make up our world were forged in stars and likely scattered by the very outflows from these feeding black holes, making us, in a very real sense, children of the galactic core. As new telescopes like the James Webb Space Telescope and the upcoming Square Kilometre Array peer deeper and wider, they will write the next chapters of this story, revealing more about the first seeds of these giants and the precise mechanics of their influence. The narrative of supermassive black holes is still being written, a testament to our endless curiosity about the universe we call home. If this journey into the hearts of galaxies illuminated the cosmic connections for you, please like this video and subscribe for more explorations into the universe's greatest mysteries. We would love to hear your thoughts on this grand dance of creation and destruction in the comments below. Thank you for watching.